Ladies and gentlemen of BlueHat 2025, trust nothing.
Hello everyone, welcome to our presentation about Windows boot security. Thanks for joining us. Whether you are a boot security expert or someone that just knows that his computer starts up somehow, we have something here for you. But we must warn you, after this talk, you will never look at your computer startup process the same way again. Quick words about ourselves. My name is Meir Bloya, and this is Netanel Ben Simon. We both work at Microsoft Israel on the pre-OS group, which is a specialized group within EPSF IL. Our focus is on low-level security research. For example, the boot, the firmware, the BitLocker, etc. Let me start with an intriguing question. What all of those top cyber groups have in common? They all have their fingerprints all over boot-related attack. We have first evidence as early as 2008. Back in those days, systems were mainly BIOS-based. But gradually, over the years, we saw the attacks move from the BIOS to the UEFI. In 2022, Black Lotus emerged. They offer full Windows secure boot bypass on a modern UEFI-based system. And this is where our story begins today. From the previous slide, you can tell that the boot is pretty important. After all, the top hacking group in the world have a keen interest in it. But why is it? What is so important about the boot? Running code at boot time essentially lets you bypass all modern system defenses, while also being stealthier and more resilient. If I had to choose, Windows Secure Boot is probably the most important security feature in Windows, because bypassing it can collapse the entire security model. Microsoft is well aware of that. This is why they heavily invested in the security of Windows Boot over the years. When Black Lotus emerged, it was my team's chance to join these efforts. We were the SWAT team. We got the opportunity to take a look on it. At this point, you know that the boot is pretty important. Let me take a few more seconds to show you the code potential from attacker perspective. To that end, I will use the famous rule of two, which basically says that if you want to write secure code, you can afford at most 2 out of 3 security risks in it. The first one is your code use unsafe input. The second, your code written in unsafe language. And lastly, your code run in high privilege permissions. You may ask yourself, where the boot in this diagram? Well, right in the middle, in the danger zone. Most of the boot code is written in C, which is an unsafe language. As we just told you, it has wide system capabilities. And on top of all of that, it's part of its functionality. It's sparse attacker control input. And we're going to elaborate about it later in this presentation. Quick words about the methodology. We've done extensive manual vulnerability research on it, and it was very fruitful. We have a series of CVEs from this research. We've done fuzzing as well, and we're going to share with you, by the end of this presentation, the different challenges when you try to fuzz such low-level components. And in the end, the most important one is we had a dynamic debug setup. It's the more important because you can do that as well. Since one of the goals of this presentation is to share with you the knowledge and tools needed to start your own research and to find your own CVEs in Windows Boot, we're going to share with you our dynamic debug setup by the end of this presentation. Ideally, in such a presentation, we would have enough time to cover the entire boot process. We would have started from powering on the device to the final user login. We would cover BitLocker, Microsoft encryption solution, secure boot, the mechanism that makes sure only signed binary run during your boot, measure boot, the mechanisms that Microsoft use to bind secret to a machine state, and other very important security mechanisms that all based on the assumption that your boot was safe. But unfortunately, we don't have enough time, so we had to make some tough cuts. Today, we're going to focus only on the essential points needed to understand our finding, highlighted in the rectangle. We're not going to cover any information that are not directly related to our core findings. And on top of that, we'll greatly simplify other areas as well in order to keep this presentation short and clear. So, without further ado, let's start with the basics. Your computer does not just magically start Windows. In our simplified boot process, we start in the UEFI, which is the modern replacement for the BIOS. Its job is to prepare the hardware and pass the control to the Windows Boot Manager. On Windows Boot Manager, you can think of as a traffic director. It reads configuration from the BCD file, and based on that, he decides what to do next. For example, in our simplified boot process, he can choose between WinLoad or WinResume, both of which, WinLoad and WinResume, need to prepare the system, and finally, load the kernel. In case WinResume selected, it will use a special file that's called Hyperfile to restore the system state, and finally, we'll reach the kernel. So, as I mentioned, our story began when Black Lotus arrived. Instead of zeroing in on one specific attack, we decided to take a different approach, a more holistic one. We decided to take all of our assumptions one by one and make sure what actually holds true. To that end, we start by enumerating all the different attack surfaces of the boot. To illustrate the concept of attack surface, let's all imagine a physical bank. It has windows and a front door. All of those are part of the bank's attack surface, places from which someone can potentially break in. In software, we have a similar concept. When we try to break some software, the first step is to understand what is these places from which we can potentially break in. So, what are the attack surfaces of the boot? The first is admin to boot, which means that if the attacker already has admin level of privilege on the machine, he will be able to communicate with different boot components on the device and potentially escalate his privilege from admin to UEFI level. Second, if the attacker has physical proximity to a device, he will be able to communicate with different boot components. And lastly, in some configuration, we have over the LAN. An attacker can potentially affect different machine boot components as long as they are on the same LAN. Now, Netanel will continue our first bug on the admin to boot attack surface.
Thank you, Meir. Okay, so we start our journey with the admin to boot attack surface. An attacker can achieve many things by escalating from admin to boot. The most notable are, first, they want to bypass security. There are many modern virtualization-based security mechanisms that makes attacker life much harder, and they all can be defeated by gaining boot-level access. Second, they seek stealth. Security tools running inside Windows, even in the kernel, cannot detect malware operating below them in the execution stack. There are many ways that an attacker with admin privileges can escalate to boot level, and we'll cover some of them. Now, let's take a closer look at an important file we've seen earlier. This file is related to the hibernation feature. Hibernation is a power-saving state that saves your RAM content and CPU context to a file called Hiberfile before shutdown. When you power your computer, WinResume loads this file to restore your system exactly as it was before. Let's take a brief view of the Hiberfile. As you can see, it is a hidden file located at the root folder of your Windows device. Its size roughly equals your computer RAM. And without this file, your computer cannot use Hibernation. In some configuration, this file will contain sensitive data. In those cases, the sensitive data is encrypted in a way that even in a special way that even a kernel-level attacker cannot read it. The Hibernation file format is quite complicated. As you can see, it contains main header describing a restoration set, and each header has its own set. Each set has its own header, and compression sets. As you might recall, here's our simplified boot flow. Let's focus on the resume flow. First, the system starts UEFI. Then it passes control to boot manager. Next, boot manager reads BCD. And it identified needs to start WinResume. WinResume then reads the Hiber file, and it validates the header integrity, restore RAM, CPU context, and deploy those settings. Finally, the user returned to their previous state. Now you got all the essential background you need to understand our first vulnerability. So let's dive right in. This pseudocode shows partially how WinResume load and parse the Hibernation file. In line 5, translated page originates from the Hiberfile header. There is no sanitization on it, and it can be fully controlled. We can set it to be any physical address we want, but it will get aligned to a page. In line 8, the physical address is converted to a virtual address. In line 16, the image header, which is partially under our control, is copied to the physical address we control as well. So essentially, this bug is almost the perfect write-what-where. In addition, now is the time to mention that bugs in boot code are easier to exploit, since many common mitigations are not implemented there on some boot components. So now to the fun part, the exploit. In ideal world, this should have been as easy as a walk in a park. But in reality, well, you'll see in a bit. We tried to edit directly the Hiber file, and we got that message. Apparently, the OS won't let us edit this file. We played with the file permissions for a while, and that didn't go well. So plan B. We investigated how WinResume knows which Hiber file to load. We found that it is configurable in the BCD. So we create our own file and point to it in the BCD. We thought that would be sufficient, right? Well, turns out that when the PC go hibernation, right before shutting down, the kernel overrides the Hiber file with a proper header. Well, that's not all of it. Resuming from hibernation requires some sort of a physical interaction with the power button. So as an attacker trying to escalate from admin to boot, it makes this attack useless. At this point, it does not look like a walk in the park anymore. We've gone back to the drawing board and to figure out what we can do. Our key new idea was that boot manager has no idea which file represents WinLoad. So we can just replace WinLoad binary path with WinResume. And now, on a normal restart, the PC will go through hibernation flow instead of WinLoad. Now let's assemble all the pieces together. we got almost the perfect right what where. We successfully managed to place our malicious Hiber file, and now we can force the computer to go through the hibernation flow without getting hibernated. Now to the demo. So we used the Windows 11 machine, 23H2, updated September 24. We opened CMD as admin. Again, admin to boot. We changed path to desktop. And we're going to execute the script that crafts the malicious Hiber file and set it in BCD. That WinResume now will work on restart instead of going to hibernation flow. The script successfully run, and we're going to restart manually. There it is. It could have been Doom, but we didn't have the time to complete it, so apologies. Now, Meir.
Thank you. Well, at this point, you all understand why we included the Hiber file in our simplified boot process. I think now it's the time to move our focus to the BCD and show you how we can use this file as well in order to gain privilege escalation from admin to boot. We start with a quick overview. The BCD is stored on a special partition. It's called UEFI system partition, or in short, the ESP. This partition also has others files. For example, boot manager, with which we're already familiar. The BCD is used only in the boot by the boot manager, as shown in our simplified boot process. The most important point for you to understand from this slide is an admin has access to this partition. He can add, remove, edit, do whatever he wants with the files are. Now, let's zoom in on the BCD itself. Here is a picture of the BCD open in the Visual BCD software. Don't worry, you don't actually need to read this tiny text. It's here for illustration purpose only. The BCD is a database. It stores Windows boot configuration data, and it's firmware independent. It has unique features. For example, setting inheritance, or it supports different value types. Its structure is very similar to the registry. An administrator can change those settings, not just by directly edit them on the disk, as we show you in the last slide, but also by using the built-in BCD edit tool. We've finished the bare basic overview of the BCD. Now, in order to understand our bug, we need to focus on one specific BCD option, the locate device. Simply put, locate device is our way to define a device that we don't know its identity upfront. Let's use a concrete example. Assuming we want to boot our computer from a VHD file. We know that this VHD contains a PES2 file, but we don't know on which volume exactly it is. So we will use the locate feature. This will tell the parser to open the VHD, and in it, search PES2 file in every partition. Locate device come in two flavors, string type and a locate type. String type is a simple one. It has a field that's called PES, and in it, we're going to have a string that contains, surprise, surprise, the PES. Locate type is a bit different. Its PES field is going to be empty, or more precisely, it's going to be in one WCAR size. We're going to provide a number to the BCD parser, and this number will help the BCD parser to extract the PES information from a different BCD element. Remember this command that we used to boot our machine from VHD? This actually creates two different objects, a parent and a child. The parent is going to be from the virtual hard disk type, and the child is going to be from allocate device type. We have many different devices, and Microsoft has good engineers. This is why they create a generic structure. This generic structure can hold all the different devices in it. The first two blue fields are part of this generic structure. This is the time to say that this is not actually all the fields of this generic structure. We put here only the fields that are relevant to our lecture. The first field, type of device, going to have what type of concrete device this generic structure has. In our case, it's going to be the local device. The second field going to have the size of this full structure. Then, in orange, we have the concrete device structure, in our case, local device. The first field type going to be either string type or a local type. The second one, type of element, going to contain a number in case of a local type. This number will be used by the parser to extract the path information from a different BCD element. Next, offset to parent, going to be null in case we don't have a parent, or going to have some number. And the last one, path, going to contain string in case we are a string type, or be empty. Now, let's see how it looks in memory when we have a parent and a child. When the parser wants to find our parent, he's going to take the child base address, add to it the offset, and this will point on our parent. Now, as you can guess, it's more difficult to work with the local type. And we probably try as early as possible to convert the local type to a string type. But how can we do it? The string type is bigger than the local type. So we're going to create a new device. We calculate its size by taking the child size, add to it the path size, and in case we have a parent, going to add the parent size as well. When we allocate this new device and copy the entire information, the child, the path, and the parent to it. Now, we have everything we need to understand our next bug. Here is a pseudocode of boot manager. This code tries to do this conversion from local type to the string type. In line 16, you can see that we take local device parent size and add it to the dev size. The problem is, it's attacker controlled, and we have no validation that dev size is not going to get integer wraparound. Then, in line 20, we use this wraparound data to create our new unified dev. And lastly, in line 24, our bug manifests itself. We copy the local device parent, which is attacker controlled, based on the local device parent size, which is also attacker controlled, into the unified dev. Unfortunately, we have no check that this size actually small enough to get into this unified dev. And this is a classic heap overflow. So, as some of you probably recall, we start with 3 different attack surfaces. But until now, we show you 2 bugs that all of them related to the first. What about the others? This is a time to mention 3 different security mechanisms briefly. It's going to be only briefly because they probably deserve their own separate presentation. BitLocker is Microsoft encryption solution. It's supposed to encrypt the user data and make it impossible to be stolen. It works together with Secure Boot and Measure Boot to deliver this promise. The thing is, BitLocker is volume encryption solution and not entire disk encryption solution. This means that your volume data are going to be fully encrypted, but not your entire disk. And what else our disk contains our nice partition, the ESP. And in the ESP, we have our nice friend, the BCD. So let's put all these pieces together. If we found a bug in BCD, we can still use this bug even on a fully encrypted BitLocker device, as long as we have physical access to this device. The reason is the volume is encrypted. The ESP is not. We can just add this on disk without any special equipment. And by that, transform ourselves from locked device to running code on its boot level. So we move in here somewhere. We have already two greens. Now to the last one. What about the over the LAN? Would you be surprised if I will tell you that our nice friend, the BCD, is also relevant to this attack surface? Well, apparently, in some configuration, in Pixie configuration, your device search the BCD online, on the LAN. And if attacker already gained access to the LAN, he will be able to send malicious BCD remotely to your device. And by this, run code kind of remotely, from no execution to boot level execution. We found one single bug that's relevant to all the different attack surfaces. We found the one bug to rule them all.
Okay. Manual vulnerability research is very effective, as we demonstrated on both WinResume and Boot Manager. However, while effective, it requires a lot of manual work. We discovered critical bugs by manually analyzing many different code paths. The reality is that the Windows boot process contains substantial amount of code across numerous components. For every vulnerability we found, there are likely dozens more waiting to be uncovered. It was the right time to add automation to this effort. This is where fuzzing helps us. Fuzzing tests the code by parsing many different inputs to find security issues. However, fuzzing boot code has special challenges. First, using traditional fuzzers such as AFL against boot application binary would require to load the boot application and fix all the dependencies to execute it. All different harness options are quite complex, whether we choose to use stub, emulation, or virtualization. Each comes with its own complexities. Second, the boot components require special environment. For example, UEFI utilities should be accessible. Direct hardware access is required, and more. In addition, different bugs can only be found on a specific boot flow configuration. The WinResume bug is a good example. It needs a specific changes to the Hibernation file during a specific boot phase. Finally, our attack targets, like the BCD, Hiber file, and the file system, have complex structure, checksums, magic fields, and much more. Simply throwing random data towards it won't work very well. Most of our complexities can be solved by choosing the right fuzzer. We chose snapshot-based fuzzer. Let's take a few seconds to understand what it is and how it solved our challenges. Snapshot-based fuzzer lets you save the system state, which includes the memory, CPU context, and much more. We can take this snapshot on every point we want, promising by this a well-known fuzzing start point. Now, let's see how we solve our issues. The first was difficult to harness. We have told you that it is difficult to handle the binary dependencies. Here, by simply using a snapshot-based fuzzer, we get most of the dependencies for free, since we have a complete virtual machine environment up and running. And as you may guess, it also solves the second and the third. The second was about UEFI utilities and other environment issues. They all solved thanks to our complete virtual machine. The third is also solved thanks to the snapshot feature. We can now take a snapshot of specific wanted flow and focus our fuzzing at this state. Unfortunately, complex structure will always stay the same. They require a lot of manual work to make the fuzzer structure aware. The best we can offer here is a lot of patience, or perhaps a very, very, very good AI agents. Now let's briefly go over the architecture of a snapshot-based fuzzer, so we'll be able to see how it all plays together. The general components are the fuzzer engine and the virtual machine engine. Starting with the virtual machine engine. We first prepare our virtual machine, and then we create the initial snapshot that will be our designated fuzzing start point. Now, let's move our focus to the fuzzer structure and see how everything connected together. It usually begins with a corpus. The corpus contains a set of relevant inputs to our target. When the fuzzer begins, they are added directly to the queue. The queue is responsible for supplying interesting inputs to the mutator. The fuzzer can either generate a new case or from scratch or apply some mutations onto an input randomly selected from the queue. It is best that both components will know our fuzzing structure in order to successfully cover it. For example, adding awareness of checksum, hashes, magic values, etc. In addition to that, the mutator job is to change interesting inputs in a way that hopefully will improve our coverage. We use several known mutation algorithms on top of the structure awareness. The fuzzing engine is responsible for initialize the virtual machine save state, inject a new test case and monitor it, and execute it, to monitor the virtual machine for crashes and code coverage, and lastly, to restore the virtual machine when the case ends. When execution is completed, we examine the results. If unique coverage was found, we save it to the queue. In the case of crash or other interesting inputs, we save it aside. Any other results are ignored. Now, before we finish, we still owe you the dynamic debug setup. So here we are. Let's examine the steps on how to do that using WinDBG and Hyper-V. We start with a fresh VM. On the host side, we go to Hyper-V, open our virtual machine settings, and disable the secure boot. Then, under memory section, we disable the dynamic memory as well. That is required for Hibernation feature to work. Next, we need to enable Hibernation by editing the virtual machine configuration. We found this nice script online that does exactly that. We set the correct VM name, run the script on the host, and it should work. Now, we boot the VM, open command line as admin, and we change the BCD configuration using BCD edit tool. We will enable debug on several components from bootloader to the kernel. After that, we will enumerate all the BCD entries and search for resume from Hibernate record. Once we found it, we will enable debug for resume using the GUID identifier. We can now go ahead and reset the guest machine. Next, we go back to the host machine, open WinDBG, and configure the network debugger according to the VM configuration. And voila, we got ourselves a working WinDBG. Thank you all for joining us today. Thank you all for joining us today. It was a long presentation full of information. We really hope you enjoyed and learned a few stuff. And we are looking forward to seeing new MSRC cases emerge from this presentation.